All right, so let's now look at example 2 right here, and we are still going to be finding the partial fractions of a given rational expression, but let's find out what else is still being special about these problems in example 2 right here. Okay, so again, for the entire example 2, any problem that I will bring up here is going to be all about we're going to find the partial fractions of. So now part A of the example, let's look at one problem. So let's start out with a rational expression, a rational function as following. So I have 2x squared minus x minus 4, and we're dividing this by x cubed plus 4x. All right, so at this point, after having some good enough experience and having seen enough, so I can start leaving some responsibility for viewers and students of mine to start taking steps of. So the first step is to find the factoring of this. And so I can just quickly do this without much explanation at this point. So the factor product of x cubed plus 4x here is simply the x and the x squared plus 4, okay, due to that common factor x that we've already had right there. Okay, but now this is where the specialty of this problem is starting to be revealed right here. So as a matter of fact, in the factor form, in the factor product of this denominator, this is all we have, okay? And so let's look at the factors that can be found in this factor product of our current denominator here. So x here is a linear factor. So x is linear. So I have to make a little underline note here. So x is linear. Okay, but this one here, it's a factor, but and it's a quadratic. It's a quadratic factor. And why do I leave that as a quadratic factor? Because I thought usually we look for ideally a linear factor in any of our factor products. But here we have no other choice rather than just leaving this as a quadratic factor. Okay, because as a matter of fact, so now there's a familiar term from algebra that needs to be brought back right here. This quadratic here is regarded as, so how about allow me to write it just a little further out right here. But this quadratic is a quadratic, but it's so it's a quadratic factor, clearly. But so now I'm trying to answer why we have to, in some problem, we have to leave it as a quadratic factor, because this quadratic here is irreducible. All right. So irreducible quadratic factor means it's a quadratic that can no longer be factored any further. Okay, so and this quadratic is simple enough. This quadratic x squared plus 1 is simple enough for any viewer and any student of mine's viewing this video lesson is to recognize immediately that we can't factor out this x squared plus 4. But then let me quickly hop to the other board and mention the following. So in case that you will run into more challenging quadratic polynomial and would like to find out whether that given polynomial there is irreducible or not, basically meaning you can no longer factor, then so recall for yourself, any quadratic is in the form of ax squared plus bx plus c. Okay, so as long do this double check right here, b squared minus 4ab. I mean b squared minus 4ac. As long as this b squared minus 4ac is a less than 0 quantity, then that will lead to your quadratic ax squared plus bx squared, plus bx plus c is irreducible. Okay, that's one general guideline, and it works anywhere, anytime. That's how you can quickly decide. How you can positively decide, how you can firmly decide determine whether your given quadratic, any given quadratic is an irreducible. That means no further factorable. Okay, so quickly in our problem here, you see x squared plus 4. Okay, in this formula, in this general formula of a quadratic, and a equals 1, b, we don't have the b term, so that means b equals 0, and this constant c is here, c equals 4. So quickly apply b squared minus 4ac, we're looking at 0 squared minus 4 times 1 times 4, and this is obviously a negative value. And that's the reason why I can say that our x plus 4 is irreducible. So that's the quick way and always valid way to check whether to determine whether a quadratic given to you is irreducible. Okay, so after all that brief algebra review right there, and of course what I'm doing here is just a brief reminder for assumingly a viewer to this lesson here is already mature at algebra or have done enough algebra. So you might have other trick to decide whether your quadratic is irreducible. But so now back to this problem. So now we're clear that the kind of factor product for our denominator here is a product where it has a mix. So the specialty of this problem is here. It's the factor product contains a mix between linear factors and irreducible quadratic. Okay, but believe me, you will never see any such thing as an irreducible cubic or irreducible fourth degree polynomial. So quadratic is the highest irreducible polynomial. Other than that, any other higher polynomial, you can always factor it down to some way. It could be challenging, but there has to be a way to factor a polynomial higher than a degree 2. Okay, and so now I need more board space, so let me erase this out. And so now let's handle this problem here, and then at the end of 1 or 2 problems, I am going to bring everybody into a generalization. Okay, so in this problem right here, then the idea is similar to how we have seen that throughout the introductory example and example 1 right here. I am going to need a coefficient on top of my linear factor in this factor product of the denominator. Okay, but further, so now, and that's all I have for the linear factor. So now and when I said that's all I have, I mean because in case your linear factor can also be a repeated factor, then you're gonna need, if that was so, then you're gonna need another constant over the x squared term. Okay, but that's not what we need here, because our factor here is only it only appears once. And now I am going to need, it's time to move on to the irreducible factor in our factor product, x squared plus 4. But that irreducible quadratic here on top, in the numerator, you need a linear. So rule of thumb that you need to add on top of your understanding now is that anytime you want to put on top, when you are doing your partial fraction decomposition step, of course, then anytime you want to, anytime that you're working on an irreducible quadratic factor, then you have to ensure what you put on top there, what you put in the numerator there, a linear. Okay, so exactly 1 degree less than the quadratic here. Okay, so bx plus c, and the naming of the b and the c here is just your naming choice right there. But that's the starting setup for us. So we want this starting rational function to equal some a over x, one simple coefficient over x. That came from our linear factor, and then we need a linear bx plus c over the x squared plus 4. Okay, and so now in that way, once I have explained about all of that, how we set it up, the general the setup of our partial fractions here, then everything goes back to how it has always been. Now we're gonna imagine if we really were adding a over x plus that bx plus c over x squared plus 4, if we were really doing that, what would happen? Okay, so of course the algebra need to kick in, and we need to make common denominators and all that. And so now I can start picking up pace here in this problem. Common denominator would be x times x squared plus 4. Okay, the a coefficient here which belong to the a over x now need to multiply with x squared plus 4. And again, it's just all that technique of making common denominator and combining fractions. The that you've learned from algebra explains for every step I'm doing here. Plus, so now the bx plus c, the current numerator of my rational expression here, bx plus c over x squared plus 4. Now I need to multiply that with the missing factor x right here. So I multiply that with x. Okay, and now we're going to start doing all the distributive laws right here. So a multiply with x squared and multiply with 4, x multiply with bx and multiply with c, right there. All right, so now in my next step, this is what I'm getting right here. I have ax squared plus 4a, and I'm adding with, for now moving on to the next term right here, x times bx is going to give me bx squared plus cx. Okay, and over x times x squared plus 4. Okay, so that's how far I'm getting right now. Okay, and so now I can further recombine like terms. So now I'm going to see that a x squared and bx squared, these two are like terms in the sense that they are all the x squared terms. Okay, and then there's a cx term, which is the only x terms, and then that 4a here, there's no x associated with that. This is the constant term. So now I can rewrite my expression as following. I'm looking at a plus b times x squared. That's my x term. I mean my x squared term. And then in my next one, I'm looking at cx, okay, as my x term, and I'm looking at plus 4a as my constant term. And all of that here is expectedly is supposedly divided by x in product with x squared plus 4. Okay. All right, and so now all of that logic remains the same. What we want here at this point is that the ax plus b as the x squared term plus cx plus 4a. We want this final added rational expression of ours to be equal to the original one, the beginning one, which now allow me to rewrite here 2x squared minus x minus 4 over x cubed plus 4x. Okay. And so, and again, notice that the two denominators here are exactly the same. It's just different expressions of that denominator. Okay, so, and you have seen this, up to this point, you have seen this argument many times. And so in that way, allow me to still, move on with somehow a faster pace here. So I need to match the corresponding coefficients and make sure they're equal, because that's the way it is. The only way for us to get what we want to achieve, what we want here, this rational expression equal to the other one, where the two denominators already equal, we have to ensure that the two numerator polynomials are equal. And the only way for those two numerator polynomials to equal is that their corresponding coefficients must equal. And so in that way, consequently, I'm producing. All right, so here we go. I'm producing a plus b. That must equal 2. That coefficient a plus b for the x squared term on the left-hand side has to equal 2, as a similar corresponding x squared term on the right-hand side. Excuse me. And so in the same way, I need c to equal -1, because c here is the x term and minus 1x, right here minus x is the x term. And so c equals -1. That's what I need as far as the matching up with the corresponding value. So c equals -1. And further, I need the fourth one, 4a from the left-hand side to equal -4 on the right-hand side. Okay, so now at this instance, I have produced for myself a system of linear equations. 3 equations, 3 unknowns, a, b, and c. Okay, but this one here is relatively easy, so I don't think anyone needs to set it up as a matrix. But as I keep saying, I leave that as an option for you. But for a problem like this, I don't think I am going to hop over to my calculator for matrices. So in case any viewer would like to go into that route for matrices, then here's your matrix. We're looking at 1, 1, so 1 for A, 1 for B, and 0 for C. So 1, 1, 0, and 2 on the other side. Okay, and then we got 0 for A, 0 for B, and 1 for C. So 0, 0, 1, and -1. Okay, and we're looking at 4, 0, 0, negative 4. So that's the matrix in case anyone really would like to find all of the values of A, B, and C from the matrix. But for me here, I'll just stick with the traditional written work right here, because, and I am, as a plan, I am about to use substitution methods here in this case, the algebra substitution methods for solving system of linear equation. Okay, not the integral substitution methods. So I already knew that C equals negative 1. We already found one answer right here. Okay, right from here, 4a equals negative 4. We can quickly divide both sides by 4 and that leads to a equals negative 1. So we found another value. Okay, and so now having a equals negative 1, I can quickly substitute that into my current equation right here. A plus b has to equal 2. Okay, and so in that way, that leads to negative 1 plus b must equal 2. And so quickly solve this equation, I can lead to having b equals 3. All right, so my work here is a lot faster than hopping over and entering that into the matrix. So any one of my viewers and my students, I highly recommend, you already have learned all of these methods. Choose the one that works best at the moment. Okay, you don't have to always go with the matrix. You don't have to always go with the substitution. So you have all of those algebra methods as, or all of those methods you already learned prior to this point as options, as tools that you use. Use the best one at the moment. So here, the best one here and getting me the fastest result is just doing the algebra work right here. Some other problem when the matrix gets big and unclear, and we use the calculator to handle the matrix and all that. Okay, and so now there we go. We found a equals negative 1, c equals negative 1, and b equals 3. So what does that mean for our result? So now allow me to swing back to my board right here. So now I need to erase this work. All right, so just like that, I am expecting, and I want this rational function of mine from the beginning to equal these two rational fractions, where we had at the beginning step, we had the missing value for the unknown value for A, unknown values for B, and unknown value for C. But now, after we successfully solved that on the other board, and so now I'm looking at A equals negative 1. So my first term becomes minus 1 over x. Okay, plus, and now with this linear on top of our irreducible quadratic, that we're looking at 3 for B, so 3x minus 1, because C equals negative 1, okay, over x squared plus 4. And now we are done. This is the same expression, I mean the same function, but written as partial fractions. These are the partial fractions of our beginning rational function. Okay, and so that is all for this part A of the example. Let's now move on to the next one. And so all right, so part B of our example, let's look at the following. Minus x cubed plus 2x squared minus x plus 1. And we're dividing this by x to the 5th plus 2x cubed plus x. Okay, all right, and so now, before we can get started, again, being able to factor out the denominator is the biggest key right there. Okay, so it looks like throughout the entire denominator of mine here in this problem, in this rational expression, then I'm having at least one common factor x throughout all three terms here. So yes, we can see, so quickly as a scratch work, x to the 5th plus 2x cubed plus x. Okay, we can factor out the x. So now I have left behind x to the 4th power plus 2x squared and plus 1. Okay, so this is a 4th degree polynomial. And then the 4th power, and just like how I said earlier in part A, when I was going over part A of this current example, and I'm saying anytime you're looking at a polynomial that's degree higher than 2, then definitely there will be a way. It may be challenged, it may be easy, but definitely there will be a way to factor. Okay, so you only when you're a degree 2 or linear factor, then that's where it's irreducible any further. I mean, I lied a little bit, but even quadratic, even degree 2, there are some quadratics are factorable and some quadratics are irreducible. That's why we have to mention that name, the irreducible quadratic, but linear or definitely irreducible, okay, because it's already the dead end. So here, this thing here makes sense that we gotta factor further, and so this is the part where you can go ahead and review your algebra, but I see this x to the 4th plus 2x squared plus 1 as a, so all that here, I see that as an x squared plus 1, but square as a perfect square. So this is really, it's a perfect square that came out from x squared plus 1, perfectly squared, okay? And then that's remaining factor in front as x is there, okay? So I have just now, and so if anyone is feeling unsure about the step, how I factor this x to the 4th, this quartic polynomial into this perfect square right here, then if you are a student of mine studying with me, then you can find a way to clarify that with me through a face-to-face meeting, okay? Or if you're a public viewer, then go ahead and grab any algebra textbook, and it has all the explanations there, okay? But so now, as an observation, so our denominator for this problem is factor. Now here's the complete factor product of that. So it has a linear factor, and sometimes be ready that there are other times where the linear factor could be having a repeat as well, but here we don't have any repeat. So there's a linear factor, and there's an irreducible quadratic. But now furthermore, you have had a little bit of this experience from example 1 right there. This power 2 right here is indicating this this irreducible quadratic factor is actually repeated. It has multiplicity 2, okay? And so now in that way, here's how I'm setting up my starting step right here. The linear factor has no repeats, so all I need is just one term for that. Just like how we have done that before. So I need one coefficient a to be over the x linear factor. That's one thing I need. But now, and that's everything we need for all of the linear factors that are being involved in this final factor product. But now, when we're now starting to step over to the irreducible, to all of the irreducible quadratic factors, then, well, x plus 1 is the only quadratic factor, but it's repeated. So now I'm going to need one term. I'm going to need one fraction, little fraction for the x squared plus 1. So it's very similar to what we have done earlier in case with the repeated power. I need one term for the x squared plus 1 irreducible without the power. So here just x squared plus 1, but without the power. And then on top of that, I have to put a linear. So we always have to put a linear on top of all of that of any quadratic factor, irreducible quadratic factor. And then we're going to need another. So here I'm running out of letters, A, B, C, so I'm going to call it E and F. So EX plus F, another linear to be over the square of my irreducible quadratic. Okay, so my irreducible here is repeated, and then it's having multiplicity 2, so I need 2 terms for that. Okay, and that's how it looks right there. Okay, so these are all being added. All right, so that's how that's how we setting up the starting step for any of these partial fraction decomposition step right here. So now, once again, just like that, I'm going to ask myself if we really are adding a over x plus that bx plus c over the x squared plus 1 and plus further with the ex plus f of the x squared plus 1 all square. Okay, if we were really adding all of those 3 partial fractions together, right, then we would need to take common denominator. Okay, and so when we take common denominator and combine the 3 partial fractions together into one fraction, what do we expect to get? For the first term, the coefficient there, the a coefficient, I need to multiply that with the complete x squared plus 1 all squared. That's what I need to do. Okay, and then for the bx plus c, all right, I need to, it's already on top of the one factor x squared plus 1, so I need one additional one and to multiply that with the other x. So I need to multiply with x and x squared plus 1. Okay, and then the last one here, I'm running a little short at space, so how about let me erase this and try to write a little narrower. Okay, so here I'm equaling. All right, so a needs to multiply with the complete x squared plus 1 with all squared, and then all of that bx plus c, I need to multiply with x and the x squared plus 1. Okay, and the last one here, the ex plus f, I just simply need to multiply with x. Okay, so this is x right here that unfortunately I'm very short in space, so allow me to write kind of like that. Okay, and so now, and all of that is over the complete factored product of the whole denominator, x times x squared plus 1 in parentheses square. Okay, and so again, this is an x here. Okay, it's an x here. Right, so ex plus f times x right there. Okay, a little hard to see. And so now I am going to go ahead and, again, I'm going to start foiling things out. So here it's going to give me x to the fourth, a times x to the fourth plus 2 x squared plus 1. Okay, that middle term, let's take it in slow step here, bx plus c times, now all of this here is an x squared, now x cubed plus x, okay, and plus with the last term here is just a simple distributive law, so we're looking at ex squared plus fx. Okay, and then I'm going to take one more step for each one of these. So there's x and then x squared plus 1 all squared. All right, and so it looks like I'm going to need the other board for that. All right, and so in my next step, let's continue. So here I'm looking at a x to the fourth plus 2a x squared. And let me carefully double check my step right here because I make errors just like anybody else. So, and plus, now I'm looking at bx to the fourth plus bx squared plus cx cubed plus cx. Okay, and then add with ex squared plus fx. And all of that there needs to be divided by x times x squared plus 1 squared. Okay, and again, let me quickly double check with my work right here. Okay, and all that there. All right, and so now let's combine like terms. So I have a to the fourth, x to the fourth is the highest powers, and then there are two like terms there. So now I am going to combine like terms. What I'm looking at now is a plus b times x to the fourth. So that's my x to the fourth term. And then now I'm looking at cubic. There's only one cubic term, so plus c x cubed. And now let's move on to my square term. There's 2a, there's b, and there's e here. So here I'm looking at 2a plus b plus e. All right, so 2a plus b plus e. And that's for the x term. And now I'm going to need to look at my x term. So far I've found my x squared. Now let's look at the x term here. And so for the x term, I'm looking at c plus f times x. And the last constant term here is going to be just simply that a right there. Okay. And all of that is over x times x squared plus 1 all squared. Okay. All right, and so at this point, now again, just like the understanding what we have been knowing, I want this final a plus b over x to the fourth, times x to the fourth times plus cx cubed plus, there's 2a plus b plus e x squared, okay, plus, and then c plus f, x plus a. Okay, I want all of this here over the x times x squared plus 1 squared. I need all of that to equals the beginning fraction, which was minus x cubed plus 2x squared minus x plus 1. Okay, plus 1. All of that is over the denominator x to the fifth plus 2x cubed plus x. All right, and so now from that, again, let's now do all of the coefficient matching right there and equating them. So there's x to the fourth term on the left-hand side, but unfortunately there's no x to the fourth term on the right-hand side of numerator polynomial. And of course, the two denominators here are already the equal expression right there. Equal function, equal polynomial. And so now I'm leading to having that a plus b must equal 0. Okay, and then I'm looking at c, and here I have to be a little bit out of order here, because there are way too many variables. So I can't. I'm having a very limited board space here to line up all the variables. So forgive me on that. But at least I can still nail down all of the equations we can set up right here. So c equals, c is matching up with -1. So c equals -1. Okay, and then I'm having, so for that term right here, I'm looking at 2a plus b plus e. Okay, and that x squared is to be, that x squared term is to be matched with that 2x squared term on the other side. So meaning this expression, this sum must equal to 2. Okay, positive 2. And then the c plus f as the x term on the left-hand side has to be matched with that -1 x term. Okay, so that means we have another equation, c plus f to equals -1. All right, and the last one here is going to be a equals 1. Because a is the constant term, it has to equal 1. My last term of the right-hand side numerator polynomial. Okay, and so we have a system of 5 equations, 5 linear equations with 5 unknowns, a, b, c, e, and f. Okay, and now we're gonna take our chance and take our time and for solving it. And so I don't think I need the matrix for this one as well. For this one either, because it's quite simple. So c is already given. C is already quite trivial, -1. Okay, it's already a value itself. A is also 1. So having a, we can quickly solve for b right here. And then having c right here, we can quickly solve for f right there. Okay, so take your time on that. And then once you solve for b and knowing a already, you can quickly solve for e coming out of that. Okay, so I'm gonna take a minute. All right, so now we know that a equals 1, so that means in this equation a plus b equals 0. We can lead to having 1 plus b equals 0, and so that leads to giving us b equals -1. So we found b equals -1. Okay, and now in the next one we know that we know a, we know b, so this equation 2a plus b plus e to equal 2 must be led to, so 2 times 1 plus -1 plus e to equals 2. And so that quickly now leads to, so that's 2 with a -1, so it's a +1 altogether here, but subtract to the other side, so e equals 1. Okay, and so we found a value for e. We already knew the value for c from the other board. Another reminder, c equals -1. Okay, so how is that useful for us? this equation c plus f equals -1. But now we know that c equals -1 from the other board, from the other result that we already had. So that means -1 plus f equals -1. So now it's leading to f equals 0. Okay, and so now, for the last one right here, we are looking at, and really we have had all of those actually. So that's everything we have. We have a equals 1, okay, c equals -1, and we have just now found the others. B equals -1, and E equals 1, and F equals 0. All right, so now we are ready to put it all together in the problem. Okay. So now I have to temporarily put this away. All right, so now our final expression is going to be as following. So this minus x cubed plus 2x squared minus x plus 1 all over the x to the 5th plus 2x cubed plus x. Okay. And then we need that to be equal to some partial fraction a over x. So and a was 1, so it's 1 over x. Okay. Plus, now we're looking at b plus c right there. Okay, but b was -1 and c was -1. So we're looking at, how about let's write it this way, minus, okay, minus x plus 1 over the x squared plus 1. Oh, all right. And then I'm looking at another one. So plus, now f was found to be equal to 0, and e was found to be 1. So now we're looking at just x over x squared plus 1 all squared. But that is how we have turned our starting complicated rational function, rational expression into, it's the same function, but now it's written as 3 terms where these are 3 partial fractions. So we have found the partial fractions of our beginning rational expression there. Okay. And so now let's finalize out the idea a little bit in a more as a generalization. And so now if we have a rational expression that starts some p of x in the numerator, and we divide, and that is over some linear, let's say a1 x plus b1 and raised to some r1. Okay, and then so there's a whole bunch of some number, a certain number of linear factors in there with some repeats. So a m x plus bm to some or m power. Okay, after factor out, and then additionally there's some irreducible quadratic with some repeats involved. So let's call that let's call those c1 x squared plus d1x plus e1. So c, d, and e, those are the coefficients to our the irreducible quadratic, and this raised to some multiplicity q1. Okay, and further, let's say some other c n x squared plus dn x plus en. Okay, and raise that to the q sub n power. All right. And of course, again, what we have here is just one polynomial, whatever that is, in the numerator. And so now that's how it. So we have to take care of all of the linear factor with the repeats first. And so we need. Okay, so we need some a1 over the a1x plus b1 plus a2 over, and these are the capital, over a1 x plus b1 square, and so on until we reach to a r1, okay, at a1x plus b1 raised to the r1 power. And then we're going to need further, and then we're going to start switching over to maybe some b. I'm going to call it b1 over the a, okay, some am x plus bm, okay, and etc., up to some brm. Okay, so we have to finish out all of the, writing down all of the terms for the linear factors. To the rm power. And then once we're done with all the partial fraction that contains the linear factors, then we're going to start advancing over to all of the irreducible quadratic. Okay, so that's not a anymore, it's c, d, and e. So c1 x squared plus d1x plus e1, and then the next one d2, okay, c1 x squared plus d1x plus e1, and then square that, and then keep advancing. All right, so that's a generalization of how we can do any rational, I mean, any partial fraction decomposition for any rational expression. Okay. All right, and now we are continuing into our example 3, and we are still doing finding partial fractions. I want anyone viewing this video lesson to have to build a solid skill in the work of finding partial fractions. So I want to introduce as many situations out there as possible. And then when I feel that my viewers, my students are fluent enough in terms of the skill of getting partial fractions, then I'm going to, on top of that, add in the actual integral work. Okay, so here in our example 3. All right, and again, we want to find the partial fractions of, all right, and then so I'm leaving that kind of hanging there. So now I'm going to introduce the problem in part A of our current example 3 right here. So the problem that I have here is as following. How about x cubed plus x, but over x minus 1. All right, so before I attempt here, let's have a closer look into this problem itself. Yes, it's a rational expression, it's a rational function. But here's a sad news right here. And the problem still wants us to find the partial fractions out of this overall rational expression. However, the sad news that I'm bringing up here is that we cannot apply the partial fraction decomposition that we have learned up until the end of example 2 for this problem. What? Why? Isn't that so useful? But why? How come we can't apply that here? So the major problem is this. If you look throughout all of the problems in example 1, example 2, plus that introductory example I've delivered at the beginning of the lesson here, then all of those rational expressions there has the degree in the numerator was less than the degree at the denominator. So let me quickly pick a random one. So if we look back at example 2, at example 2a, for example, the problem that we did there was 2x squared minus x minus 4, and we put that over x cubed plus 4x. So this was a problem that we did. So we don't need to restart the problem again. We went through the partial fraction decomposition process on this one, and we got to whatever answer that we've got. But see, right from the beginning, the whole reason that allowed us to apply the partial fraction decomposition process on this problem was because, you see, the degree of this polynomial in the numerator was less than, how far less than, doesn't matter, but in order to apply the partial fraction decomposition the process, we have to strictly be in that requirements where the degree in the numerator is less than the degree of the denominator, which was the case in any of the example problems back throughout the entire example 1 and example 2, including that introductory problem. Okay, but so now what? So now we're stepping out of that zone. Now when we're stepping out of that requirements, I mean, we need the numerator to be less degree, but now our numerator is being, so anytime that we have a numerator equal degree or a higher degree than the denominator, here's how we actually handle it. So we're still gonna find partial fractions, but we won't be able to apply the partial fraction decomposition that we've learned previously. Okay, so, but it's worth to mention, really worth to mention. So we're still gonna find partial fractions. Okay, but we're just not doing that through the partial fraction decomposition method. Okay, so here's how we're doing it. And it's going to be a surprise for anyone viewing this video once I mention it. The only way to get partial fractions of this is to really divide out. We divide the numerator by the denominator here. Okay, so how do we divide polynomials? That's where your algebra skills comes back in again. The specific skill I'm looking at here is the skill to divide, to carry out a long division for polynomials. Okay, so let's set up the problem as following. So I really want to divide x cubed plus x right here, divide that by the x minus 1. Okay, so here's how we're setting it up. The denominator is here, or maybe let me set that in a separate space so that I can save all the space for the actual final answer right here. So let's step over to my example, my other board. All right, so here's how the long division process works. And please allow me to keep this as minimal as possible in terms of the explanation, because the skill I'm going through here is entirely algebra, and anyone viewing this video is expected to be familiar with this process already. Okay, so I'm just only gonna go through the process, but leave the explanation in a minimal basis right here. Okay, so all right, so here we go. Now I'm gonna draw that roof sign, and I put the denominator outside of the roof right here, x minus 1. Okay, and my x cubed plus x, the numerator, is being inside of the roof. Okay, and so the final quotient, the step-by-step quotient that we found, that we're going to find, is going to be put in here. Okay, so first step now of this long division process, I am going to take that first term and divide that into the first term of my denominator. So x cubed, including the signs right here, including the coefficient being positive 1, divided by x, including the coefficient here, gives me x squared. Okay, and so now allow me to introduce this, based on a very minimal basis of explanation right here, because I'm assuming that anyone viewing this video is already familiar, at least done this once or twice in your mathematical learning process right there. Okay, and so now after I've had that quotient, I am going to multiply the x squared for each term here. Okay, for the entire denominator. So x squared times x gives me an x cubed. X squared times negative 1 gives me an x squared. Okay, so that's what happens when you multiply this quotient x squared with the whole x minus 1. And so now I am going to subtract out carefully. Now, so the way I approach it does appear slightly different with some textbooks. The way some textbooks present this out there, as well as the way some professors present it out there. But I do this for a reason where it reduces the amount of confusion, because a lot of times if I switch sign too directly right here, then I'm gonna lose some students in terms of their understanding. Okay, so I'm gonna really tear it down to every single little step like that. But now subtracting out. So now when we subtract an x cubed, subtract x cubed is a 0 out. Okay, and then just like that, And so we don't have the x squared term to subtract with this. So technically think of that as a 0 subtract minus x squared. So 0 subtract minus x squared leaves behind for me a positive x squared term as a remainder. Okay, but we're not done yet. So there's still this x term right here from our numerator. So x minus 0, because there's nothing else left in this x cubed minus x squared right there. So we're looking at plus x. Okay, so far this is the remainder. So think about if we divide, and again, I shouldn't have to repeat this because you should have learned that back in your algebra, but this is the numerator. So when we divide that into the denominator here, we got a quotient, and subtracting out is to change for some remainder. And now if the remainder is still higher degree or at least equal degree with this denominator, that means it's a sign that we have to move on and continue dividing out. So now this is our current remainder, our current leftover of this division process right there. So now I'm going to again start out. Only need to pick that first term and divide that into the first term in my denominator. So first term divided by the first term. But when multiplying back, we're always going to have to multiply for all terms. So positive x squared divided by x, including all the signs and coefficients, then we're looking at a plus x. X squared divided by x is a positive x, so it's plus x. So now, plus x. So that x term, again, I only need to multiply that x term for each term throughout all terms in my denominator here. So x times x is an x squared, okay? X times 1 times negative 1 is a minus x. And so now I'm ready for another subtraction, okay? And so x squared minus x squared is a 0 out, okay? X, and then x minus a negative x gives me a positive 2x, okay? And so now let's check again. And we don't have anything else to subtract, so this is the remainder so far, and we're done with that subtraction, basically. But now, should we proceed further? So let's check again, and I mentioned that earlier. The degree here of this current remainder is still equal to the degree in the denominator. So that means we should continue further. And so in that way, now I'm going to proceed as, and this is the only term I have. So I'm going to take that only term as the first term supposedly, divide that by x right here. I'm looking at plus 2. Okay, so plus 2, because 2x divided by x is plus 2. So now 2 multiply. So now I'm going to take that 2 and multiply that throughout each term in my denominator. And so now again, 2 times x is a 2x. Okay, but 2 times negative 1 is a minus 2. And we subtract out again. Okay, so our final remainder. Okay, so allow me to rewrite this because it looks a little too tight in space right there for me to write. Okay, so now when we subtract out, then we're looking at a final remainder. So 2x minus 2x, 0 out right here, but then nothing, 0 minus 2 minus 2 gives me a positive 2. Okay, so this positive 2 right here is right now our most recent, our most current remainder. But then this most current remainder is obviously or apparently less degree, because this is degree 0. Less degree than the denominator here. So now this is a good sign where we stop the long division process right here. Okay? And this is our final remainder with a positive sign. Remainder being positive 2. So what does that mean right here with the long process? So now I'm back on my board. On my other board right there. So that means after we apply the long division process right here, and let's look one more time, look back at the work right here. This quotient we have found over here. So think of any division problem right there. After a division, we got a quotient and we have some remainder. So this is our quotient. And then we have some remainder left. Okay, so the quotient here, let's observe that carefully. X squared plus x plus 2. And this is a positive 2. Okay, they happen to be the same 2, but then they don't mean the same thing. Okay, and so now that means after the long division, we broke down our rational expression into the following. All of this equals x squared plus x plus 2. That's the quotient part. And then what do we do with the remainder? The remainder was positive 2, as we have seen that here, positive 2. And so now I have my legal rights, I have my mathematical rights to write this as plus 2 over x minus 1. So we take that remainder and simply put that over the denominator there. And that's how we express our the overall rational expression into a quotient plus a remainder as a simplified rational expression here. Okay, and so, but now, so where are the partial fractions? We've been spending so much time learning about the partial fraction, and all of a sudden in this example 3, I let viewers, I let students of mine into a different, completely seemingly off track right here, but this is our partial fraction. It's all of x squared plus x plus 2 right here over 1. So, and this is, or now you can see this as a one standalone polynomial itself, and here is another partial fraction. So these are all partial fractions, or you can think of that as x squared over 1 plus x over 1 plus 2 over 1. These are all little partial fractions. And then there's another partial fraction that looks a little more legitimate. Okay, so that's how we find the partial fractions in the case, in those situations where the numerator has degrees either equal or higher degree than the denominator. So we definitely have to carry out the long division process. Okay, so let me bring up another situation right here. So let's now, I'm going to leave part A here the same. Let's look at part B right here. All right, so the problem I prepared for everyone to look at is x to the 4th minus 2 x squared plus 4x plus 1. And let's divide that. And that is over x cubed, okay, minus x squared minus x plus 1. Okay, and so I'm not intending to reveal the partial fraction process, so allow me not to show that part. I mean, I'm not intending to reveal the long division process here, so allow me not to show that work here for this problem. I have already had the long division process done before I wrote this, before I start recording this video lecture right here. So just simply allow me to write this down, the final answer down, and then I want to make some clarification, okay, on top of that. And so, all right, so as far as breaking it down right here, immediately after the long division process, this is what I get. I have x plus 1 as the quotient. So right after the long division process, so these are our two partial fractions, as if you want to see it that way. Plus, now the remainder for this now is going to be 4x over all of that x cubed minus x squared minus x plus 1. Okay? And so now, here's the thing. So we've had a long, we carry through, I mean, you can pause the video and check for the long division, apply your long division process to convince that you should land into this answer right here. And as I said, I'm not intending to reveal the long division process for any of the problems. So I already spent time with part A right here, but in part B, I'm just going to save everyone's time by just get straight into the answer. But this answer, I'm now telling you, it's after the long division process to get this. So this is the remainder. But so here's the thing. So I call these the partial fractions, but we can actually even, you see, have a closer look at this. Okay, have a closer look at this final little fraction that came out from the remainder of the long division and putting that over the whole denominator. Back in part A, and the reason I still leave part A here is that back in part A, we definitely cannot apply the partial fraction decomposition process on this one any longer. Take a moment to think of the reason why. The reason I won't be able to apply the partial fraction decomposition process on this any longer because this was already so at a dead end. And what do I mean by so at a dead end? See, the denominator itself is already a linear polynomial. So we cannot factor a linear polynomial any further, or we can't even divide that anymore. So this one right here, we can't, this is already at its very partial fraction. Okay, it's the least level already. We cannot reduce any further. But then this one here, admittedly, the numerator is less degree than the denominator, and it's in terms of the long division process, we're done right here. But now the good news for this, we can actually apply the partial fraction decomposition process for this problem right here. Why is that? Because the denominator, remember I said in the earlier part of this lesson that only when your denominator is a linear or an irreducible quadratic, that's where you stop. Otherwise, see, right now the degree is still 3, then we can still proceed. So you can produce a separate problem to find partial fractions out of this, which now, as to be to reveal the truth, this thing right here, I use that as example part. I use that as we can roll back to example 1 part B right here to see how I did the partial fraction decomposition on this particular problem right there. So I purposely designed these examples so that somehow they are connected, so that the viewers can understand a little bit better right there and make better connection. So the partial fraction decomposition process can apply here. So now in practical situation out there, a lot of time when you're given a problem where numerator is higher degree or equal degree with the denominator, then first thing is to apply the long division process. The long division process comes first, and then once you are at that final fraction where you are looking at the remainder over the whole denominator, if your denominator here after the remainder is still with degree 2 or higher, then you can still apply the partial fraction decomposition process further on that particular fraction right there. Now don't do anything with this, okay? And so that's the whole intention of introducing this example 3 right here, for you to understand that we're still finding partial fractions, but sometimes we have to slightly take things in a little bit different directions. Sometimes, like part A here, we don't have to apply the partial fraction decomposition process at all. Whereas in some other situation, we have to take long division process first, and then we apply the partial fraction decomposition the process after. Okay. And so now in that way, I have just now looked back at the result I've done back in example 1 part B right here. And so let's put it all together. Let's put all the pieces together. So now, after we apply the long division process, and after that, if we would apply the partial fraction decomposition process on top of this, and this is the final ultimate final answer for all this. X plus 1 remains the same, but the partial fraction decomposition process broke this down into further as so I've had minus 1 over x plus 1, okay, according to the answer from example 1b right there, and then plus there's a 1 over x minus 1, and plus a 2 over x minus 1 all squared. And this is where we can no longer find any sub-partial fraction anymore. So this is the final dead end answer for breaking this down as partial fractions. So this is a partial fraction, that is a partial fraction, and these are all partial fractions. Okay, and none of these can be broken down any further. And that's the whole point of bringing up all of these little examples again. All right, and now we are ready to see how useful that partial fraction decomposition method can be for an integral problem, for a problem where we're taking integral. Okay, so now we are at example 4, and we are ready for that. All right, so in example 4 here, I'm going to spend the entire example 4 evaluating indefinite integral. Okay, so let's look at part A right here. So how about part A of my example? Let's say I want to evaluate the following integral. We are looking at x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx. All right, so here we go at our first definite integral where we can apply the partial fraction decomposition process. So really, I designed any of these problems here to connect with the earlier examples. So before I proceed here, if anyone have a closer look at this problem, you can notice that the actual rational function that I am attempting to find the indefinite integral right now came out from example 1a already. So I already showed the work, because obviously this is now a problem where we have to apply the partial fraction decomposition process to break this down into partial fractions, so making it easier for our work. Okay, so in exam, go ahead and refer back to the earlier part of the lesson where I was going over example 1 part A over here. All right, and so let's see how useful that was, that we spent some time looking at the partial fraction decomposition there. So after going through the entire partial fraction decomposition process, then this rational expression of ours right here, okay, turns into something like this. So according to the work we have done back in example 1a, then we're looking at 1 over 2x, okay, plus 1 over 10x minus 5, okay, and then minus 1 over 10x plus 20. So one overall rational function, but now we broke it down to 3 separate little fractions, okay, and then on top of that, this is now an integral problem. So we had one term here, one rational expression, but now we turn it down into some, and that's the whole reason of doing partial fraction decomposition and going through all that algebra work, because we want to break our expression into small terms. Each one of these is a lot smaller expression and easier, much easier to handle. All right, so here we are now. So we have learned previously that taking an integral, we can do that term by term. So that means I can produce one separate integral for 1 over 2x dx, okay, and one separate integral for this term 1 over 10x minus 5. And notice any of these has some kind of common factor right there, okay, and that's the dx. And then minus, so the next term is a minus, and then there's the integral 1 over 10x plus 20 with the dx. Okay, so that's the first easy step, and one more step to explain how I see that. But see, 1 over 2x can be thought of as a 1/2 times 1 over x. See, this is the same as 1/2 times 1 over x. That's how I'm seeing this. Okay, so in that way, recognizing that we have a coefficient there, then I can rewrite my first term, and it's still right now as an integral. So it's a 1/2 being pulled in front. Okay, and then to make the integral even easier to recognize and easier to recognize. So 1 over x dx. That's, how easy to recognize that is for the integral of 1 over x. Plus, now I see this, if we can see that we have a common factor of 5 in the denominator. So this similar experience with that algebraically. Now I can pull out that 1/5 in front of the integral, okay, as a coefficient. Because there was a rule that allowed us to bring the coefficient in front of an integral, okay? And so now we're looking at 1 over 2x minus 1 dx, okay? And with this right here, I can see that I have a common factor being 10 for here, so I can pull that out front, so it becomes a minus 1/10 of the integral, okay? And then I have 1 over x plus 2 dx. Okay, and so now in the next step, of course, we are ready for the 3 terms right there. And so you see now, I don't usually do this, but and believe me, the more experience you have done this, the faster it gets. See, I'm going to consider one separate integral for this. This is going to be a 1/2 natural log of absolute value of x. Okay, and then that's just one term, so I'm holding on to the plus c right there. For the last term, it's also an easy one. 1 over 10, okay, just on that separate term right there, 1 over x plus 2 dx, we can quickly see that this becomes a 1/10 natural log of x plus 2 in absolute value, okay, and we can refer to the my video lesson on the substitution method to see how I can quickly see this, okay. And the last one right here, and the middle one actually, it's so it's 1/5, and the integral. Okay, and so right now I'm treating any of this as just some quick scratch work right there. So 1/5 with the integral of 1 over 2x minus 1 dx. See, it's substitution again. I suggest substituting that 2x minus 1 for you right there. Okay, and then viewers can go ahead and pause the video and process on your own work right there. But the final integral for this, the 1/5 is still there, but the final integral should have another 1/2 but times natural log of 2x minus 1. Okay, or altogether this is here a 1/10 natural log of 2x minus 1. Okay. All right, so now at this point we are ready for putting it all together right here. So that's just a quick little scratch work. I am going to go back to my first board right here. All right, and so now these are just the steps. So my final answer now for this. So all of that integral together, we are now looking at the first term here gives me 1/2 natural log of x in absolute value. Okay? The next term, the middle term here really was a plus, right? So now it becomes a 1/10, okay, times natural log of 2x minus 1. Okay, and the last term was a subtraction, so minus 1/10 times natural log of x plus 2. All right, so now we have done finding all the three antiderivatives or the three indefinite integrals on all the three different terms. Then at the final step right here, don't forget to have that plus c. All right, so this is how easy that is to find the indefinite integral on a complicated rational expression like that. And the major process here was there was that partial fraction decomposition process that we applied here to bring our the rational expression down to multiple terms like this, multiple partial fractions. Okay. All right. So let's look for a couple other problems here in the same example. So the next one here, I'm going to call that part B. All right. So the integral in part B that I'm looking at here. So let's look at this integral. So part B right here, 4x over, and now it's x cubed minus x squared minus x plus 1, and with a dx. All right. Okay, so again, in order to speed up the process a little bit, now I'm reviewing that truth. Like this rational expression was the one we worked on from example part B, where we took the partial fraction decomposition process on this rational expression. Okay, and so that means so the point now is that when we're integrating this problem, when we're taking the indefinite integral of this problem, then we can rewrite our rational expression here according to the result we found in example 1b. Then we found the following partial fractions. So that was 1 over x minus 1 plus 2 over x minus 1 square, and then minus 1 over x plus 1. Okay, so these were our partial fraction that we found, after example the 1b right there. So these are the three partial fractions for that particular problem. And then now it's a one integral on three separate terms. And again, just like how we did that in part A, we can break it down and work on the problems term by term. So it becomes, and allow me to switch that term to that middle position, and then that last term with the square to be the last one, because I want to put some consideration on that, the term here at last. Okay, so here's how it looks. So there's one separate integral for 1 over x minus 1, which is easy. Okay, there's a subtraction, one separate integral for the 1 over x plus 1. These are all the easy ones. Okay, and then plus, now that is a 2 as a coefficient, 2 times 1. So I can leave the 2 in front right here. So 1 over x minus 1 square dx. Okay, all right, so that one here is easy, and just in the experience you have seen through my substitution method, or we have seen that through the earlier work like that. So this becomes a natural log of absolute value of x minus 1. Okay, similar term with the minus sign. So here, minus natural log of x. I accidentally made that pencil stroke right there. So natural log of absolute value x plus 1 plus. All right, so let's do a little bit of scratch work to find out what this is, okay, before we put that in there. Okay, so again, I'm going to navigate over to my other board and treating my other board as scratch work. Okay, so on this particular one, 1 over x minus 1 all square here, dx, okay? I can just simply see this, and again, refer back to my video lesson on the substitution method. This is regarded as x minus 1 in the parentheses to the negative 2 power dx, okay? And so I'm going to make a u substitution for u equals x minus 1. Okay, so that's my u substitution. And so after making that u substitution, then du dx equals 1, or du differential equals dx differential. Okay, and so what that means, this problem becomes all of that there inside of minus 2 power is a u, so u to the negative 2 times now dx now is substituted by du. Okay, that's just quickly how we can handle this problem separately. And then so that becomes, so now with this simple integral, now we're ready for finding that final antiderivative for this particular term right here. So it's minus u to the negative 1 power, right? And then I don't need the plus c yet. Okay? And then that means it's a negative 1 over u, or u itself was x minus 1, so it's negative 1 over x minus 1. Okay? It's negative 1 over x minus 1. So just on that particular problem, it gives me this as the antiderivative, or as the indefinite integral. So that means now I'm ready to put that piece back into that individual piece back into my current problem. So there was a 2 here, and the problem in the end turns out into a negative. So here it's going to become that. So I shouldn't have that plus now any longer. It's now minus 2 minus 2 over x minus 1. Okay, and now all of that here, we put a constant plus c right there. All right, so this is my final answer for that. Okay, so that's part B of our example. And so once again, the long process, the partial fraction decomposition process was done back in example 1b right there. So, but in practice, if you have one problem at start, then right at the beginning, then after writing down your problem, then you do your somewhere between these two steps, you're gonna take your time doing the partial fraction decomposition, and then make another final conclusion. This integral will equal to all of those, will equal to an integral on all of those partial fractions, and proceed on as an integral problem. Okay. All right. So let's now look at part C of the example. And so the example in part C here, let's say we want to find the integral, the indefinite integral of 2x squared minus x minus 4 over x cubed plus 4x dx. Okay. And again, to speed up the process, I purposely designed this problem, this integral problem, based on the problem that we worked in. This now example, this expression, this rational expression here came out from example 2, part A, right there. Okay, so you have seen how I worked through the partial fraction decomposition process back in example 2, part A, right here. So now with all that work there, so according to example 2, part A, then this integral, this rational expression here has the following partial fraction decompositions. It's going to be, now allow me to write as following. So 3x minus 1 over the x squared plus 4. That's one partial fraction. Okay, and then minus 1 over x. Okay, so now we broke it down into two separate terms. And that's one integral. All right, and so that's now making it separated into two separate integrals. One of them is for the 3x minus 1 over the x squared plus 4. And the other one is 1 over x. Okay, that's one integral on 1 over x. Okay, and so in my next step, I am going to leave a gigantic space right here to, ready for the final answer of that one, because I want to spend some time working on scratch work with this little guy. With this term right here. So I'm gonna eventually go over to the other board. But the second term here, the second integral, is an easy one. So it's supposedly giving me a minus natural log of x in absolute value, and then plus c. But now this gigantic space right here, let's find out on scratch work or on the other board as a separate work right here how we can find this particular indefinite integral. Okay. All right, and so let's now just specifically focus on this 3x minus 1 over x squared plus 4 dx. Okay. So at first sight, it might look a little struggling for any of us, or problematic for any of us. But here's the thing: take advantage of that being two terms here. So that means I can separate this down into even further little terms like that. So one of them is a 3x over the x squared plus 4. That's one fraction. And then minus, because of that minus here. Okay, and then 1 over the x squared plus 4 dx. Okay, so this first one right here, we can do a little substitution rule over here. So I can let u equal the x squared plus 4. Okay, so that means du here equals 2x times with the differential dx right here. Allow me to start skipping some steps, because you've seen all of this argument back in, all of this logical reasoning back in the video lesson where I explained about the substitution rule over here. Or in other words, du over 2x here equals dx. And so now this integral can be done as, so this is a 3 right here, and x right here, and or I am moving a little too rush right here. So 3x, and then there's u right here, and the dx is substituted by du over 2x. Okay, so the x cancels out, the x cancels out, and that gives me, so just that 3/2 out front and 1 over u du. And so in the next step, it gives me a 3/2, okay, natural log of u. And u was that x squared plus 4 right there. So really this is 3/2 natural log of x squared plus 4. And x squared plus 4 is always positive, so I don't even think we need parentheses. We need absolute value here, but let's just keep it that way right here. So everything I'm doing here is just for that first term. Okay, so that first term here, now I'm going to write it. So that's, again, scratch work. So all of that there really is just 3/2 natural log of x squared plus 4. Okay, and now let's find out what that integral is going to be. All right, so there was a different video along with my substitution methods video lesson right there that I explained that this 1 over x squared plus 4. Now notice that the 4 here is 2 squared. So this integral over here, I want you to notice this 4 right here is the integral of x squared plus 2 squared. Okay, so we wrote that for a purpose right there. Okay, so from the result we have done in that video that I introduced here, that I mentioned here, right? I introduced this kind of a technique in that video there. But so this overall thing here becomes a 1/2, okay, and then tangent inverse of x over 2 right there. Okay. So now all of that here becomes now I can erase the gigantic space right here. So this one fraction that we spent so much time working on the separate scratch work on the other board now becomes here it gives me 3/2 natural log of x squared plus 4. Okay, and then subtract, we're going to minus, there's a 1/2 tangent inverse of x over 2. And then of course subtract natural log of absolute value of x plus c. And that is our final answer for this entire problem right there. All right. It will always take some good amount of patience to go through any of these integral problems right there. Okay, so for me, in order to stand here in front of a camera teaching, I've gone through a lot of integral problems right there, and to build my own experience. I'm only saying it's just to build my own experience so that I can now become a teacher in teaching. And I'm not saying that I have already done all integral problems out there yet. There are still integral problems out there that's super challenging for any math instructor as well. Okay, all right. So let's now look at another one. So just keep looking at to see how we apply the partial fraction decomposition process into any of these problems right there. Okay. So now I'm going to erase this. All right, so let's look at part D of our example. Okay, so here's the problem. So with our part D, we're looking at the integral of minus x cubed plus 2x squared minus x plus 1. And we divided that by x to the 5th plus 2x cubed plus x. Okay. And so again, I intend that this problem, at least this rational expression in our integral here came out from example 2 part B right there. So in example 2 part B, I worked out the steps to apply the partial fraction decomposition to find, and we already found the partial fractions out of this, the overall rational expression there. All right, so now I can say that from the result of example 2 part B right there, right? Then our integral turns into the following. So from one rational expression, now we can rewrite our rational expression here as an integral of 1 over x minus an x plus 1 over x squared plus 1. Okay, and then plus an x over x squared plus 1 all squared. Okay, and then so with these three terms, but really it's just one same rational function there. Okay, but now written as three separate partial fractions. Now we are ready to take the derivative, the indefinite integral term by term. Okay, and so that means I am going to separate it down into 1 over x dx. Okay, so we learned a little bit of experience from the earlier problem that we've done. So with something like this, even though already a partial fraction, but we can still write this into two separate little fractions. So it's algebraically it's going to happen as following. There's a minus sign right here, so be careful with that. So it's minus, so we have an x over x squared plus 1 dx. Okay, and then it's a subtract again. 1 over minus, and then 1 over x squared plus 1 with the dx. And then the last one single term right here. It's the integral of x, and I realize I wrote all these terms too largely. So now I have to shrink them down a little bit so to make enough space for myself. Okay, so 1 over x squared plus 1 with the dx, and then the last term plus the integral of x over x squared plus 1 all squared with the dx. Okay, all right, so first term is easy. It's natural log of x. Okay, this term here in the middle, okay, I highly recommend to apply the substitution method if you decide to work on your own separate space. I don't recommend rushing step anyway, but I just want to write it down directly. Write down the immediate answer here so anyone can recognize that, can follow along, and then at the end of the problem I'm going to swing back to the other board and quickly show how we work that out. Okay, but for now, as a suggestion, we substitute x squared plus 1 for a variable u. Okay, and that's how it is. And so in that way right here, this integral would become minus 1/2, okay, x squared, natural log of x squared plus 1. Okay, that's what it is. And then this term right here is simply the inverse tangent of x. And then this last term right here is simply going to be, and again, I am going to apply that u substitution on the x squared plus 1 right there. Think about it that way. And so here I'm looking at a 1/2 times x squared plus 1 to the negative 1 power, or let's write it this way, times 1 over, and that actually here becomes a negative 1 over x squared plus 1, which is 2 power 1. And all of that here, don't forget, plus c. Okay, so let me explain a little bit of how that happened and how this happens. Okay, so this is our final answer, and I should have had that in a box right there. Okay, but now I'm going to quickly swing over to the board to explain how that happened, in case anyone would like to know. All right, so for the one that we had x over x squared plus 1. Okay, then again, I suggest that we take the substitution u for x squared plus 1. So du equals 2x, du dx equals 2x, and we can rearrange this to become du over 2x to equals dx. And that's the substitution part right there for that. Okay, and so now from that point, then this integral becomes, the integral here becomes x over u, okay, and the dx here is substituted by du over 2x, okay, and the x got cancelled out, okay, and the 1/2 right here is pulled in front, so we're looking at 1/2 multiplied with the integral of 1 over u du. Okay, and so in that way, now it becomes a 1/2 natural log of u. And so, and this is only one term of the whole bigger problem, so I'm not going to do the plus c here, but u itself was chosen as x squared plus 1. So here we're looking at 1/2 natural log of x squared plus 1. And that's why back in my problem, just that term here, x over x squared plus 1, it gives me 1/2 natural log of x squared plus 1 in absolute value. And then the minus sign came out from the sign before that. Okay, so let's now look at this particular one right here to see how it happens, how it came from here down to that final answer, even though, so this was the final answer, but I want to explain a little more about that. Okay, so right, and so now for that integral, and I'm ignoring the sign right here, I'm just looking straight into the integral itself right here. So x squared plus 1 all squared in the denominator. So x over x squared plus 1 all squared. Okay, and so I am going to choose u, to substitute u for x squared plus 1. Okay, so the same thing here, that means du dx equals 2x, and we can rearrange this as du over 2x to equal dx. Okay, and so now from that point on right here, then my integral becomes x. It didn't get a substitution for that. Here it's a u squared, and here it's a du over 2x. Okay, and I can, just like usual, I can cancel the x away, and there's a 1/2 left behind, so 1/2 being pulled out front. 1 over u squared du, or essentially the same as the u to the negative 2. So now we're ending up with a very simple integral like that. And so that's 1/2. And it's the overall here becomes a negative u to the negative 1 power. Okay, after taking the antiderivative of that. All right, and again, this work here is just only the work that explains one term among all the three or four separate terms like that. So I'm not going to do the plus c here in this scratch work like that. Okay, but the final answer here, we should bring back the x variable. So now I'm looking at minus 1 over 2, and before I do that, minus 1/2, and then the x squared plus 1 to the negative 1 power. But then this means, this algebraically equals negative 1 over 2 times x squared plus 1. And that's the whole reason why I've had the answer as shown earlier in the final answer there. And that's the one. And so at this point, really, I can also write it as following. All of this here is really just a 1 over 2 times, and in parentheses x squared plus 1 right there. And then I now would have more space to write my plus c plus the constant at the final answer. All right. And now let's look at another problem in example 4 over here. And this last one, this one here, this next one I'm bringing up here could be the last one, for the last one. And I believe after this one here, anyone viewing the video has already seen enough, and will start building your own confidence and building your own experience in doing these problems right there. Okay, so part E. So let's now look at the integral of x cubed plus x over x minus 1 dx. Okay. All right. So now if anyone seen my earlier example, then this rational expression here came out, and I worked on that to find the partial fractions of this rational expression in example 3, part A right there. Okay, because I just want to save time and effort for viewers of my video. So now we can refer back to example 3A to look at how I done the long division process and possibly apply any partial fraction decomposition to get the partial fractions. And so the partial fractions we came up with back then in example 3A over here gave us the following. So now x cubed plus x all over x minus 1 is the same as x squared plus x plus 2, and plus an extra term, an extra fraction, x minus 2. I mean 1. Okay, so now we have 1 term, 2 term, 3 terms, and 4 terms. Okay, that's according to the work we have done back in example 3 problem A right there. and dx. And this is an integral on 4 separate terms. And now it's making it surprisingly simple. So here I can now legally, according to the indefinite integral rules, the rules for taking integral, I can do a separate one for x squared. I can do a separate one for the x term. I can do a separate one for the constant term 2. Okay, and I can do a separate one for this fraction 2 over x minus 1 dx. Okay, and notice this here can be written as 2 times the integral of 1 over x minus 1. That's to make it easier. Okay, so now one by one. The first integral here gives me 1/3 x cubed. Okay. The next one here gives me 1/2 x squared. The third one here gives me 2x. And the last one here, understanding that as 2 as a coefficient times the integral simply of 1 over x minus 1, then I'm looking at plus 2 times natural log of x minus 1 in absolute value. And then all of that plus c. And here's our final answer. And I don't think I need to present any scratch work for any of these little ones.